In the last few lectures, we were looking at the features of turbulent flows. As I said, turbulent flows occur at high Reynolds numbers. There is a transition from a laminar to a turbulent flow. These involve large fluctuations in the velocity in all three directions. They are necessarily three-dimensional. These fluctuating velocities transport mass, momentum and energy due to convection. Convection due to fluctuations is what is called dispersion. And this mechanism of dispersion is much more efficient than molecular diffusion, and for that reason turbulent flows are highly diffusive and highly dissipative. They have a range of length and time scales, okay? And we had calculated the smallest scales from the requirement that all of the power that is input at the large scales has to be dissipated by viscous dissipation at the smallest scales. That was one consideration. The other consideration was that the smallest scale features do not depend directly on the length and the velocity of the large scales. Okay. It depends only upon the rate of dissipation of energy per unit mass, that is the whatever energy is input at the large scale has to be dissipated at steady state. That is one requirement. The second requirement is that the dissipation is due to viscosity, and therefore it can the small scales depend on the energy dissipation rate per unit mass epsilon and the kinematic viscosity. Okay. And based upon that, we had got the smallest scales, the smallest Kolmogorov length, time and velocity scales here, okay, as well as the strain rate. Okay. These are RE power minus 3/4, minus 1/4 and minus half smaller than the large scales. Okay. Therefore, the smallest eddies have a length that is RE power minus 3/4 smaller than the large scales in the limit of high Reynolds numbers. The velocity is RE power minus 1/4 and the time scale is RE power minus half. Strain rate in the smallest eddies is much larger than in the large scale eddies. It is RE power plus half larger. What that implies is that the energy dissipation rate in the small scales is much larger than that in the large scales. Okay, the energy dissipation rate in the smallest scale eddies is much larger than that in the large scales, and it is equal to the energy input per unit time in the large scales. Okay. So, the picture that we had was of a cascade of turbulence, where energy is put in at the large scale due to the pressure difference that is applied across the ends of the pipe. Due to an instability of the laminar flow, there are eddies of different sizes that are created all the way from the large scale, the pipe diameter and the mean flow velocity, down to the Kolmogorov length and velocity scales. At the Kolmogorov length and velocity scales, the Reynolds number based upon the Kolmogorov scale is 1. The Reynolds number based upon the large scale is much larger than 1, but the Reynolds number based upon Kolmogorov scales is 1. That means at the Kolmogorov scales, the inertial and viscous effects are comparable. Energy input at the large scale is dissipated by viscosity at these smallest scales. So, the flow itself creates smaller and smaller scales such that at the smallest scales the energy input is equal to the energy dissipated, and that is how a turbulent flow is sustained. Energy is put in at the large scales, the flow creates smaller and smaller scale eddies until all of the energy is dissipated at the smallest scales. I had shown you that for a turbulence in a gas, the length scale of the Kolmogorov eddies is much larger than the length scale for the gas molecules, the molecular scale, that is the mean free path. For gas molecules, the molecular scale is the mean free path, the velocity is the RMS velocity, and the kinematic viscosity is proportional to the mean free path times the RMS velocity. In these arguments that I make, I will assume that there are proportionality constants which we are neglecting, okay, just to compare the orders of magnitude, not the we are not worried about constants that are order 1, we are only comparing the orders of magnitude. So, if I write the ratio of the Kolmogorov scale in the mean free path and then substitute the mean free path times the RMS velocity for the kinematic viscosity, the ratio of the Kolmogorov scale and the mean free path is equal to R e power 1/4 by the Mach number. Incompressible flow, Mach number is much smaller than 1. Okay, the velocity is much smaller than the speed of sound. So, the Mach number is much smaller than 1. That is the limit in which the continuum approximation is valid, when the flow velocity is much smaller than the molecular fluctuating velocities. In that case, Mach number is much smaller than 1, Reynolds number is large, so the ratio is large. Okay. Similarly, if you compare the time scales, the ratio becomes R e power half by Mach number square. Okay. So, that is also much larger than 1. So, turbulence is a continuum phenomenon. Even the smallest turbulence scales are much larger than the molecular scales in gases, in liquids also, because the molecular scales in liquids are much smaller than the molecular scales in gases. So, what we had discussed so far are the general characteristics of turbulence. Okay. Now, let us examine the turbulent flow in a pipe, okay, in some further detail. Velocity profile in a pipe is more plug like at the center and has sharper gradients at the walls in comparison to a laminar flow at that same Reynolds number. Okay. A laminar flow at the same Reynolds number will have a slower gradient at the smaller gradient at the wall, and it would have a higher curvature at the center, okay, at that same Reynolds number. And I said there are large cross stream velocity fluctuations which tend to transport momentum across the pipe. Okay. Velocity fluctuations at the large scale, they are anisotropic. The fluctuating velocity in the flow direction is much larger than that in the cross stream directions. At the smallest scales, these are isotropic. The velocity fluctuations take place, have roughly the same magnitudes in all 3 directions for the smallest Kolmogorov scales. Both the mean velocity and the fluctuating velocity have to satisfy the condition that they decrease to 0 at the wall. At the wall of the pipe, we have a no slip condition. So, therefore, both the mean velocity and the fluctuating velocity have to decrease to 0 at the wall of the pipe, okay. Which means that momentum transport to the wall has to be entirely due to diffusion. If the fluctuating velocity decreases to 0 close to the wall, momentum transport at the wall has to be due to diffusion, because there can be no velocity perpendicular to the surface. Even fluctuating velocity has to be 0 perpendicular to the surface at the wall due to the no penetration condition. Okay. Therefore, the velocity close to the wall has to decrease to 0 fluctuating velocity. That means that the shear stress at the wall is entirely due to viscous effects, okay, because the fluctuating velocity magnitude has to decrease to 0. Recall that while we were solving for the velocity field in the pipe flow, okay, we had also solved for the shear stress, okay, and the shear stress balance equation basically told us that the shear stress is a linearly increasing function, okay, from the center to the wall. Okay. The shear stress, okay, tau xr is a linearly increasing function from the center to the wall. Okay. In the region close to the wall, okay, in the region close to the wall, okay, you would expect the velocity fluctuations to decrease to 0 in this region where there is a sharp gradient. and the thickness of this region is small. As I said, the velocity gradient close to the wall is larger, but there is a plug flow near the center, and this transition between these two regions takes place close to the wall. So, in this region the shear stress is approximately equal to the wall shear stress. Okay, in this region the shear stress is approximately equal to the wall shear stress. This region where momentum transport close to the wall is by viscous diffusion, where the fluctuating velocity decreases to 0 and therefore momentum transport is due to viscous diffusion, is what is called the viscous sublayer. Okay, it is called the viscous sublayer. Okay. And in this region the wall shear stress is equal to the viscosity times the velocity gradient close to the wall, okay, because close to the wall the velocity fluctuations have to decrease to 0, stress transmission has to be only due to momentum diffusion within this viscous sublayer. Okay. In this viscous sublayer the velocity is much smaller than the velocity in the bulk, because the velocity decreases to 0 at the wall. What is the velocity scale in this viscous sublayer? Okay. You can get a velocity scale just from the consideration that because this viscous sublayer is very thin, the stress is approximately a constant. Okay. The stress varies very little within this viscous sublayer, and therefore this is basically a constant stress region. Okay. So, based upon the stress and the velocity, the stress and the density, you can see that from dimensional analysis a velocity scale can be written as tau w by rho whole power half. Okay. This is what is called the friction velocity. Okay. A velocity scale that is determined from the wall shear stress and the density close to the wall, this is what is called the friction velocity. Okay. And if you focus closely, okay, on the region close to the viscous sublayer, okay, the velocity in this region is increasing linearly. Okay, the velocity in this region is increasing linearly. Okay. In the viscous sublayer, the velocity is much smaller than the average flow velocity. Okay. That means that you can scale the velocity scale in the viscous sublayer by the friction velocity alone. Okay, so the relevant velocity scale for the viscous sublayer is not the average flow velocity. Okay, you recall that when we solved for the bulk flow in the pipe, we had defined the scaled velocity as the velocity divided by the average flow velocity. The velocity in the viscous sublayer is much smaller than the average flow velocity, and the velocity scale in the viscous sublayer is the friction velocity. Right? Therefore, the velocity scale in the viscous, the scale velocity in the viscous sublayer can be defined as, okay, it is usually defined as Vx. Okay, is equal to Vx by V star. Okay, that is the scaled velocity in the viscous sublayer. Okay. What is the characteristic length scale for the viscous sublayer? Okay. The characteristic velocity scale in the viscous sublayer is the friction velocity, ratio of wall shear stress and the density power half. In the viscous sublayer, viscous effects are dominant because the fluctuating velocity has to decrease to 0, and therefore momentum transport has to be due to molecular diffusion. That means that the length scale for the viscous sublayer, okay, the characteristic length scale for the viscous sublayer has to depend only upon the kinematic viscosity and the friction velocity. Okay, the length scale for the viscous sublayer has to depend only upon the kinematic viscosity and the friction velocity. It cannot depend upon the pipe diameter and the average flow velocity. It has to depend only upon the length and velocity scales close to the viscous sublayer, as well as the kinematic viscosity. Therefore, this from dimensional analysis has to be nu by V star. Okay. Within this viscous sublayer. Okay. Therefore, if I write a distance, okay, W, which is equal to the pipe diameter minus r. Okay, so r is the radius of the pipe, small r is the distance to some point within the viscous sublayer. Okay. The distance W is the distance from the wall, which is r minus r. Okay. Distance from the wall within the viscous sublayer. Okay. And the scaled distance from the wall will be equal to r minus r by this length scale L in the viscous sublayer, which is equal to r minus r by nu by V star. So, even though the flow in the bulk of the pipe is turbulent, when you come close to the wall from the no slip condition, the velocity has to decrease to 0 at the wall. Therefore, viscous effects have to become dominant compared to inertial effects within a thin region close to the wall. The large scale flow velocity and pipe diameter are not relevant for this. Okay. What is relevant is only the conditions close to the wall, that is the shear stress that is exerted by the flow at the wall, okay, and the kinematic viscosity, because transport is due to viscous diffusion at the wall. From this we can get a friction velocity, which is the wall shear stress divided by rho to the half. Okay. Recall that the wall shear stress has dimensions of density times velocity square. Kinetic energy per unit volume has the same dimensions as stress. So, the velocity scale close to the wall is the friction velocity. The length scale can depend only on the kinematic viscosity and the friction velocity, which is nu by V star. Therefore, the velocity and length scales are Vx plus is equal to Vx by V star, the dimensionless velocity, and the dimensionless distance from the wall. Okay. Dimensionless distance from the wall is W plus is equal to r minus r by nu by V star. Note that the wall shear stress, okay, tau W, okay, is equal to mu dV x by dr, okay, with a negative sign. Okay. Substitute, okay, these expressions, okay, mu V star, okay, dV x plus by dW plus, okay, and in going from W plus to this I will have by nu by V star. Okay. Okay, I am just substituting, okay, in the expression for Vx and r. I am replacing Vx by V star times Vx plus, and r, the derivative with respect to r is negative. Okay. So, I am just replacing this by W plus here. Okay. So, this is equal to mu V star square by u dVx plus by dW plus. Okay. And the kinematic viscosity divided by the I am sorry, mu divided by nu is just equal to rho V star square. Okay. Okay. Note that I had defined the friction velocity. I defined the friction velocity as V star is equal to root of tau W by rho, okay, which implies that rho V star square is equal to tau W. Therefore, this tau w and rho v star square on the left and right cancel, and I find that the expression for the velocity gradient at the wall dvx plus by dw plus is equal to 1. Okay. That means that if I am scaling it by the wall shear stress and the friction velocity and the length scale nu by v star, the velocity gradient close to the wall is universal, it is equal to 1. Okay. This implies that the velocity increases linearly with respect with is proportional to w plus close to the wall. Okay. So, therefore, you have a straight line for the velocity close to the wall where Vx plus is equal to W plus. Okay. Now, this is a requirement in the viscous sublayer. Okay. What about when you go outside of the viscous sublayer? What expression for the velocity do we get from experiments? Okay. So, the experimental results are shown in a graph which is called the von Karman plot. Usually it is plotted as Vx by V star. Okay. Vx is the mean velocity profile in this case. Okay. So, Vx is the mean velocity, that is, I have averaged over the fluctuating velocity. This is plotted as a function of log of W plus. Okay. You should plot it linearly to get a straight line slope of 1. It is usually plotted as log, and because of that you get a curve that looks something like this in the viscous sublayer. A straight line in a linear plot, okay, versus Vx by V star. Okay. This would be 1. Okay. So, let me write it in a dashed line. This would be 1 in a linear plot. This would be 1 in a linear plot. Okay. In the von Karman plot, it is plotted as a function of log, which is why you get this curve over here. Okay. This happens up to a value of W plus of approximately 5, okay, approximately 5 here. Okay. From a value of approximately 5 to a value of approximately 30, okay, you get a line, straight line. Okay. So, this is the viscous sublayer. Okay. And from a value of 5 to a value of about 30, okay, you get what is called the logarithmic layer. Where the velocity follows approximately a logarithmic profile. Okay. That velocity Vx plus can be written as 1 over a constant 1 over kappa log of W plus a constant. Okay. So, you get a universal viscous sublayer when you define it as scale velocity by friction velocity, and then you get a universal logarithmic layer. Okay. For a smooth pipe, okay, kappa is approximately 0.41 and C is approximately 5.5. Okay. Okay. This is for 0 less than or equal to W plus less than or equal to 5. This is from 5 So, that is the universal velocity profile that we see, okay, in this von Karman plot. Okay. It is a linear up to the viscous sublayer. That is a requirement because the fluctuating velocity has to decrease to 0, stress has to be viscous, and therefore, the velocity gradient has to be a constant when in this constant wall shear stress region. Beyond that point, you can show using asymptotic analysis that the velocity has to be a logarithmic function of position. That calculation is outside the scope of this course, but nevertheless, this logarithmic dependence is seen in experiments. I should caution you here that these constants are approximate. This is an active area of research where there is progress that is continually made, and these constants by latest estimates are slightly different from what the classical theories which were proposed for this viscous sublayer and Kolmogorov and the logarithmic layer. However, these are still approximate constants that can be used to make estimates. Okay. These are still approximate constants that can be used to make estimates. Okay. And then you have a bulk flow near the center of the pipe. Okay. So, this region very close to the wall is the viscous sublayer. Okay. W plus less than 5. 5 to about 30 is where you have the logarithmic layer, and then beyond that you have a plug flow where there is virtually no change in the average velocity with respect to position, okay, a plug flow. Okay. So, this is the structure of the flow in a pipe. Even though the flow is turbulent, very close to the wall, it has to become viscous dominated because fluctuating velocities have to decrease to 0. That happens when W plus is less than about 5, or the distance is less than about 5 times nu by V star, okay, where nu by V star is this length scale, okay, close to the wall. V star is the velocity scale based upon the wall shear stress in the region close to the wall where the stress is approximately a constant. Okay. So, these are the characteristics of flow in a pipe. And finally, I will end with a problem of how the friction velocity is related to the flow Reynolds number. Okay, the flow Reynolds number and the friction Reynolds number, how are they related? And how can we estimate the friction Reynolds number from the flow Reynolds number? Okay. So, what is the friction Reynolds number? For pipe flow with Re is equal to 10 power 5 and friction factor okay, 4.5 into 10 power minus 3. Okay. What is ratio of wall unit? By wall unit I mean this wall length scale, okay. By wall unit I mean this wall length scale, okay, and the pipe diameter. Okay. So, how do we calculate this? Okay. The wall shear stress, okay, we know that the friction factor okay, friction factor okay, is equal to the friction factor. This recall is the fanning friction factor. Okay, this recall is the fanning friction factor. Okay, which means that tau W is equal to rho V average square by 2 into F. Okay. Recall that when expressed in terms of the friction velocity, this can also be written as rho v star square. Okay. From this we find that the friction velocity is equal to V average root of f by 2. Okay, so that is the relation between the average velocity and the friction velocity through the friction factor. Okay. Reynolds number, okay, so let me write this as friction Reynolds number rho v star d by mu into V star by V average into root of f by 2. Okay. It is equal to Re root of f by 2. Okay. So, in this case the Reynolds number is 10 power 5 and the friction factor is 4.5 into 10 power minus 3. Okay. So, this you will end up getting as 4743. Okay. So, this is the friction Reynolds number Re star based on the friction velocity, the pipe diameter and the viscosity. Okay. So, this is the friction Reynolds number. Okay. What is the length of the wall unit? L is equal to nu by V star. L is equal to nu by V star, which means that the ratio of the wall unit, okay, the ratio of the wall unit and the pipe diameter is equal to nu by d V star. This is of course just the inverse of the friction Reynolds number. This is of course just the inverse of the friction Reynolds number, and this in this case is equal to 2.1 into 10 power minus 4, okay, 2.1 into 10 power minus 4. Okay, I just take the inverse of this Reynolds number. Okay, I just take the inverse of this Reynolds number and I get 2.1 into 10 power minus 4. So, the ratio of the viscous sublayer, the wall unit, the viscous sublayer is of course about 5 times this. Okay, so, the ratio of the wall unit and the pipe diameter is 2.1 10 power minus 4. So, if your pipe had a diameter of about a centimeter, the viscous sublayer will be approximately 2 microns times 5, which is about 10 microns at the wall. Okay, so, that is the characteristic length, that 10 microns at the wall. That thickness is small. Okay, it's about 1,000 times smaller than the pipe diameter at a Reynolds number of 10 power 5. However, it is still much larger than the molecular scales. Okay, 10 microns, molecular scales are about 0.1 to 0.01 microns for gases and of the order of angstroms for liquids. Okay. So, the viscous sublayer thickness is very small. The logarithmic layer is about 5 to 6 times that, and beyond that is all the bulk. So, this is the summary of the qualitative features of the flow in a pipe, okay, of a pipe flow. Okay. So, I have completed the discussion of the laminar flow and the turbulent flow in a pipe. Okay. Thank you.